Previously, I had stubbed in a framework that I could use to display the status of power on self tests. In this video, I'm going to show some actual implementation of some of those tests that I have made it through so far. And so what you're seeing in this initial little video clip is just showing my system now basically going through the post process. And what I am doing as part of this is I am checking every byte of RAM and making sure that I can write to it and read it back. I'm also going out to the PPIs, writing a configuration and trying to retrieve that configuration. And I'm going to discuss a challenge I've run into with that specifically. The VIA, same thing. I'm writing something and reading back as far as configuration to that. And the math coprocessor, I'm actually sending it data input for a calculation of an area, checking the result to make sure it matches what I expect. And then I am also doing a test of the PIC. And then at the end of that, I say post complete. And in the event of a failure, I will flip the screen white with black text, so it kind of pops out a little bit, and I know that it fails right away. You'll also notice that as it goes through the RAM test, I am basically counting from the top 64K of RAM down to the bottom 64K of RAM. And on the 8 character 7 segment LED display, what you're seeing is that it's showing which of the address ranges is it currently running through. So which of the segments, which of the 64K segments is it running through, starting at the top and working the way down, all the way down to the bottom of the RAM. And if all that stuff passes, hopefully you see what's on the screen here. It shows that everything has passed. In the rest of this video, I thought I'd just walk through some of that assembly. And so if that's something that interests you, stay tuned. And if not, maybe I'll catch you in the next video. But I'm going to proceed and just kind of take a look at what do we have here for assembly. What am I doing to actually do these tests? And I'll throw out that good old note that I am still pretty new to this x86 assembly. So while some of this probably works, it may not be ideal, and definitely feedback is always welcome. So if you have suggestions on ways to improve something, or something I'm doing doesn't look like it is really even the way to do it, let me know, and I will make updates accordingly. So here's the latest version of my assembly that I'm using. And I first of all put just a reminder. So this is the physical memory map that I'm using, which will be important later because I'm going to be doing some testing of RAM. And you'll see that I'm going to basically have to work all the way from 9FFFF down to 0. And I'm going to actually test every one of those bytes. As I continue down, I have a data section, and maybe something I would point out in that data section are some vars. I set aside the first K of memory, 1K of memory just for my interrupt vector table, but then I set up a variable here, memtesttemp, that I'm going to use kind of as a temporary location that you'll see later when we start testing out RAM. So maybe make a quick note of that, and I'm going to collapse this section for now. My main code starts within the text and at top, and probably the first thing maybe I should point out, I have updated where my extra segment points, and by default I'm now pointing to this F000, or in other words to the very top of my ROM space, and that'll be F0000 as far as where ES will point to. So anything that I write to that I can easily get to just by referring to ES, which has been pretty handy. But later in my testing, I'm going to use this ES for other purposes. So maybe another mental note there to take. But then in my code, I initialize, for example, the LCD and the SPI and the SD card, etc. I then eventually get down and I call post tests. And if I go down to post tests, it's just calling a series of other tests. And I thought I'd walk through each of these quickly and just kind of give you an idea of what I'm doing. And the first one I'm going to start with is just the RAM. And so, like I mentioned before, I want to test this entire range, and my goal is to actually write a byte to every one of those addresses basically, and read it back and just validate that what I wrote is also what I read back, and that should be a decent test at least. So first thing I do is I just write out to my OLED screen, and so to do that I've made up some equates up above, so I can say cmd print status OLED. That's the SPI command, and then this is the parameter to go with it. So I'm going to say that I want to write to my OLED that I'm starting the RAM test, and then I send that out to my Nano, which then writes the appropriate data to the OLED screen. So that's just filling in that OLED as I go. And you'll see these types of calls throughout that will then add in a fail or a pass, depending on the status of where I'm at. I use BX just for a quick little keeping track of which segment of memory, which 64K segment of memory I'm going to be testing. And I have to test from basically the 90000 to 9FFFF down to the 876543210. And so those are my 10 64K segments, giving me my 640K. And then I basically have a loop within a loop using BP and SI. And one of these is simply used to count down. Start at FFFE. I'm going to read a word, and then I'm going to drop down to C, FFFC, read a word, drop down, and I'll keep dropping down. And once I loop all the way back to FFFE, I know I'm done with that 64K segment. And then I'll decrement the segment from 9,000 to 8,000, and I'll repeat this part of it. And that's what you're going to see down below. The other thing I do is I use this extra segment to point to one of the 64K segments at a time. So I'm going to start out with the 9,000, and I put that into SI, and I move SI into my extra segment. So at this point when I start out, keep in mind ES is pointing to my physical 90000 address spacing. And then I write out to my little 8-character 7-segment LED display that I'm starting with a 9. And this just says write to the digit 4, which is the 5th character from the right, and write out a 9. And so I write a 9 onto that. And then I continue into here and I say, okay, well, let's go out to this ES, which when we are at this point, ES would be 9000. And grab whatever BP is, and BP I'm starting out with FFFE. So really I'm going to 9FFFE. That's the highest word location in my RAM. I'm moving that into my A register, and then I'm going to write that out to this variable, this temporary variable, which actually that might be a minor bug. I better fix that. Up in my data. Initially I was doing this 1 byte at a time, but then I changed it to words, and so this probably should be a DW. So I'm going to set aside a word, not just a byte. Okay, sorry about that. Coming back down then, when I get down into this, then I take whatever was in that top spot in memory and I write it into that temporary location, because I'm going to need to put it back when I'm done with this test so that I'm not trashing memory as I go. And then I just grabbed an arbitrary word of data that I'm going to write into that address location, the very top of RAM. And in this case, I'm just doing a hex db. It's just a pattern. It really doesn't matter. I just want something I can write and read back. So then I go ahead and I put that into the location, into this temporary, or I read that value, I write it into the location in RAM, and then I grab that location in RAM and write it back into A, and then I compare what's in A with db just to make sure it matches. And I also move then my backed up data back into A, and then I put that back into the original location. So there's a whole bunch of swapping around of memory here, but what I'm basically doing is I'm going to a spot in memory, I'm reading what's there, storing it in a separate little scratch location, then I'm writing a new value to the memory, reading back the value, comparing it to make sure it matches what I'm looking for, and then I restore the original value that was in that RAM location. And if that comes back and that compare doesn't match, then I jump down to a fail, and I have a fail down here. Otherwise, I'm going to keep on going. So then I'm going to subtract 2 from BP, And BP, remember, we started at FFFE, so that's going to drop me down to FFFC. It's not going to be 0, so then I jump back up and I do it again. And I keep doing that until I'm down with the 64K. When I'm down with the 64K, I drop down to the 8,000, so 80000 would be the physical address, or the 8,000 segment. And then I do this 64K chunk again, and then I go to the next, down to the 7,000 64K chunk, and I keep repeating that over and over and over. And if anywhere along the way this doesn't read back the memory that it expects, then it jumps to the failure. But if it gets through all of that and everything has matched, then I go ahead and I jump down to pass. And so if it fails, I write out a failure message. If it passes, I write out a pass, or the procedure is called finish, but it writes out a pass message. And then I get out. And when I'm getting out, there's maybe a couple of things here along the way. I am updating this LED with where I'm at as far as which of those 64K segments I'm currently in. So that'll just simply count down. It'll count from 9 down to 0. And then down here at the very end, I basically write out to the position that I've been using to put a dash in there, so it goes back to the original startup value. And also at the end of this previous loop, I end up writing an FF to the LED, and I didn't want to try to add extra logic, so I just clean that up by writing a dash back into it's the next, or the previous, the one to the right. That character ends up with a dot in it because I sent an FF to it, but I just put a dash back in. So these are just basically setting my 8-character display back to all dashes at the end of all of this. And then I have to put my ES back to what I want it to actually point to for the rest of my code, which is back up to this F000 segment. So that's the routine that I wrote that I think is running through 64K at a time. It's going through all 10 segments, so I get my full 640K. I'm backing up memory, I'm writing to the memory, I'm reading from the memory, I'm testing it, and I'm restoring the original value. And I think that is all working fine. But if you see something here that just doesn't seem right, let me know. There's a lot of learning I've had to do in my assembly coding as I've been going through this, but it's been good to write that routine. Then I go in and I test PPIs, and interestingly enough, I ran into a challenge with this. I thought the approach would be pretty simple. I would write out to the configuration register, and then I would read back from the configuration register and just make sure that what I wrote comes back. And that works fine if I'm using an Intersil 82C55A. As I read the datasheet there, I can write that register, the control register, and I can read it back. And that was the datasheet I was working off of. The actual part I'm using right now, though, is an NEC. And after I just could not get the reading back to read back the value I was expecting, I was just always getting something that was wrong. It wasn't what I was expecting. I went to the datasheet for the NEC version, which is not a C version. It's just an 8255 that I'm using right now. And it does not support reading back from the control register as far as I can tell. It shows that I can write to it, but it actually shows in a table that I cannot read from it. I have a C version that's en route that I think I'll have in the next week or so, which is an OKI. But I also looked at its data sheet, and it also does not support reading back the control register, which I think that's weird, or kind of odd, strange that it doesn't support that. So right now, the way it sits, unless I can get a hold of the Intersil, the rest of this code just isn't going to do me any good. I'm not going to have a good way to test those PPIs. Now, obviously, at the end of the post, I send out a beep. I have my LCD and my keyboard input. All of that's really easy to tell if it's working or not. So I'm not too worried about having a post test for a power on self test for the PPIs. But it would be nice to write out the control register, read it back before I get too far into anything else in the system. So maybe I'll see if I can track down one of these others just to see if they support that. And of course, I have tested my code, and I know I cannot read back the control register on the NEC. I'll try it on the OKI when I get those in, but based on the data sheets, I'm not hopeful there. But if I had this one, then I think the rest of this routine probably is fairly valid. Again, I write out that I'm starting the test, And for now, I'm just skipping the whole test and jumping to the pass. But once I get, if I had this in hand, then I would just simply come in here and I'd say, okay, I want to write out to the PPI's control register. Here's the configuration, which is previously defined as this byte here. I want to write that, and then I would send that out to the configuration port. I'd read it back in from the configuration port, and I would compare it. And if it matches, that tells me I'm at least writing and reading a register, the control register on that PPI just fine. And then if I make it through that, then I would normally just let this keep on going into, I would jump out to out 1, and then I would continue with PPI 2, the exact same thing. And at the end of that, I would then get out of the routine if it passed. And I've got failure messages or pass messages along the way. So for now, this is more of just a not really doing anything in my specific implementation. It's all the code is there, and if I can get a different PPI, then maybe I can activate that code. For now, I'm just having to pass them the way it sits. And if someone knows that there's some other trick to read back the control configuration from either of these two, especially this OKI, that's what I'm going to end up using once I get those in. Do let me know, but as far as I can tell, I could not get back values I wanted, and reading the data sheet, I noticed a huge difference in how the inner cell shows I can read it back, and these other two in the identical type of table in the data sheet shows I cannot read back. I can only write to that register. So that's my PPI routine. Then I get into my VIA routine, something pretty similar. So I just tell it I'm going to start that test. I load up all ones, and then I put those ones out into this IER register of the VIA, which basically is which interrupts are enabled or not. So I enable all interrupts, and then I basically read that back. So I write out that I want all interrupts enabled. I read it back, which should bring back all ones, and then I add 1 to it. So now I should have all zeros, and then I check, do I have all zeros at that point? And if I don't, something went wrong in this writing reading above, and I jump to fail. When that's done, then I load up a 0, which the first bit is telling me either set or disable. And so this says basically set all of these on. This says disable all of the following that have a 1. So disable all my interrupts. And then I write that out, I read it in, and then I compare it. And when I read it back, it'll always give me a 1 in this first, and it's saying you have the following interrupt set. And since I said disable all, this is going to say you have enabled none. And I compare that, and again, if it does not match, then I jump to not equal down to a dot fail. Otherwise, I jump down to a dot pass. So that's the routine I'm using for the VIA. Then I get up here and I have my math coprocessor. And as I look at the math coprocessor, basically I'm going to calculate the radius of a circle. And this was an example from one of the books I've referenced in previous videos. But basically I have a radius of 91.67, which I now store in a section at the end of this, which is this ROM, this read-only data section. So I have R defined down there, and this is what it's defined as. 9167 is equal to this 42B75770A, and then it actually gets stored like this in the ROM because it's a little endian. But I then go out and I say grab me those values out of R, put them into move it into AX. And actually, as I'm looking at this, I think these were leftovers from when I was printing out that data, and I deleted the print lines, but I left these in. These are not doing anything, but R would have this data in it. And then I come down here and I say go ahead and initialize the math coprocessor, basically load up R, and then I want to square the radius. When this gets loaded, it gets loaded into a register, basically the top of the stack of those registers on the math coprocessor. I load up pi and I multiply pi times my previous squared r. So that gives me my area, which then I go ahead and store that into a variable called area. And at that point, this is what should be in there, and that's what it equals to. And physically in RAM, it might show up like that. And I found that I needed a slight delay here, so I call a delay, and I can maybe do some more tweaking with that, but it seemed like the delay helped as I was working with this. And then I go in and I compare. So go out and grab half of my result here, grab the word, compare it, and if it doesn't match, fail. Then I grab the other part of the result and compare it, and if it doesn't match, it fails, and if it made it through those, it passes. And then the same type of thing here. Show me my message that either I'm failing or passing. So that's the math coprocessor testing. And then that gets me down to the PIC. So the PIC, as I look at that, this on a cold start, I noticed it required an extra just kind of run through of some data that I write and read from it. So I just put in some calls quick that just write out and read back from the PIC. And I don't actually do any testing. I just write some stuff, read some stuff, and that's what this first part is. And I'm just calling that a little warm up. But then I actually get to my test procedure, and this is referenced in the IBM BIOS Technical Reference Manual. And one of the books that I'm using as a reference referenced it and reprinted it with IBM's permission. So this is a routine that I pulled from that, and basically I'm going to refer to port 1 on my PIC. And previous videos on the PIC, I talked about some of these different types of control words I can send to it. I need to send it what's called OCW1. That's the control word I'm going to send. But basically, I'm going to send it a 0. So I'm going to send a 0 to this, and I'm going to unmask all interrupts. In other words, all interrupts are being enabled with that. And then I read it back, and then I OR it with itself. And if it is not 0, there's something wrong. So I come back and I say, if it's not 0, jump to a fail. So basically, I wrote a 0. I should read back a 0. I kind of OR it with itself. Again, should end up with a 0 as far as what I'm testing with. If it's not 0, I failed. If it is 0, I keep on going, and I write out an FF to it. And so that is disabling all interrupts. And then I read it back in, and at that point I should have read back in all 1s. I then add 1 to it, and if I add 1 to all 1s, that should roll me back around to 0s. So when I do this add, I should be back at 0, and this is saying if it's not 0, then go ahead and fail, otherwise continue on to pass. So this is just another way of testing, writing out, reading back, and testing that I'm getting the things that I would expect to get. And that is the end of my PIC test. So in my case, I'm doing the RAM, the VIA, the MathCo, and the PIC. Those are all actually testing. I am skipping the PPI test because of the types of PPIs I have don't support the reading back of that configuration port. I did consider maybe connecting PPI 1 to PPI 2 on one of the ports I'm not using. Maybe just put a resistor, a couple of resistors connecting a couple of bits so that I could write from one, read it in the other, reverse it around. But I thought, I'm not too worried about it. I didn't want to go through that effort. So for now, I'm just simply not doing a real effective test on the PPI. But like I said, maybe I can get a hold of the different PPIs from Intrasil that will support that. So that's about it. And this code I will have posted. So in the link in the video, just follow that if you want to kind of actually go through and read through this in more detail. I have been doing other cleanup on this, and as you'll see, I've got quite a bit of code up here just as far as friendly names for things so that I can use those instead of having numbers buried all over in my code. I did also at the very end add in this RO data section, and in it I have moved all my SPI commands now, so those are no longer in line with the SPI code. They're down here in the ROM, and I then point ES to this RO data section, so I can easily move straight from here into wherever I need it in RAM. I don't have to constantly be switching some of my other segment registers around. So that's really nice to directly copy from ES, which is this down here. And you can see that in my code. But I've got my SPI card stuff. I have a bunch of my strings that I put down here. I've got all my keyboard key mapping down here. And there's that R that I was using earlier. If you have any feedback on any of these test procedures, or if there's other things I should be testing, I could definitely consider adding some additional tests, so let me know. Thanks for watching.